So, hi friends, this is Shomik Bishas. You are attending my class on that circuit theory and network. Today we are attending the fourth class of that active and passive filter. So, today actually we are concentrating on that parameters to be identified for filter design both in that low pass and high pass. So, actually in the previous past 3 lectures what I have told, what is the image impedance, what are the parametric views to be transferred, what are the condition for that short circuit and open circuit condition, and what is the pass band and stop band, and what is the phase constant and what is the attenuation constant. So here we are applying these theoretical views to consider this particular case of that filter design where that constant k type and other type of filter is given. So here first thing that we are about to calculate, the term is called as image impedance, this one. So image impedance equals to Z1 Z2. So if they are truly resistive, we can say it as R0 square. So it is considered as K. Now what is K? K is basically the root over of Z1 and Z2. Now if it is only L and C is there, LC type filter, so obviously that characteristic impedance or the input impedance or the image impedance, that Z0, we can write it as root over of L by C, right? Now so the image impedance, how we have to write and how we have to calculate for LC type, it is clear to you. If it is something, if both are L type, so what is the final value? It is omega square L, so omega root L. So that particular value is having one omega inside, so it is changing its value, and obviously that type of filter will not exist because that R is a function of omega, and as long as the omega is changing, the R is also changing. So the image impedance, if obviously changing for different frequency of operations, so this particular filter is quite tricky to handle. Well, the next part is called as a cutoff frequency. So what is cutoff frequency? In that cutoff frequency, actually it is a particular prime point from where the pass band shifted to stop band or the stop band shifted to the pass band. Now what is pass band and stop band? If you are representing the entire, say suppose if you are having a transfer function of a particular network, so from the control system engineering you know what is the transfer function and what is the Laplace transformation. So obviously if you are doing some Laplace transformation, you will be getting obviously one S term in the transfer function, that S equals to j omega. So if you are replacing these particular things in the j omega plane, so obviously you are getting one frequency response. So one frequency response is a very important character for a filter analysis. So here if you are getting one frequency response, so it should have one stop band, it should have one pass band. So the transition between the stop band and pass band, it is called the cutoff frequency. Actually graphically you can say it is a straight line, just stop band switch to pass band, but practically it is not a straight line or directly downfall is not there, rather it is a transition. So the cutoff frequency is what? For the condition already we have considered that for Z1 equals to 0 and this Z1 plus 4 Z2 equals to 0. For Z1 equals to 0, we know that omega c equals to 0, okay, and fc equals to 0, but for Z1 plus 4 Z2 equals to 0, we will be getting that j omega l plus 1 by j omega c equals to 0. So fc equals to 1 by pi root over lc. So the limit of fc is basically ranging between this 0 to 1 by pi root over lc, okay. So this particular part is the concept of the cutoff frequency, fine. So after having this sense of image impedance and the cutoff frequency for the low pass filter design, we should go in the next part, that is the attenuation and the phase constant you have to calculate. Now already I have shown you that the pass band and the stop band, you should have that alpha equals to 0, it is a pass band, and stop band equals to alpha equals to this. So now the Z1 and Z2 value is known to you, you are just putting this value inside. So obviously it remained as that f by fc. Why? Because you can easily calculate that what is the value of Z1 and Z2 if you are putting this value Z1 and Z2. So it is omega L and j omega c. So obviously omega will be cancelled and L by 4c, so obviously it is that fc can be easily put inside this particular one. So the attenuation constant is here 2 cos h inverse 1, it means cos h f by fc, or you can write it as 2 cos of h inverse root over of omega square lc by 4. Already these things has been calculated. Now what is a phase constant? Now the phase constant is basically, as you can see that already I have discussed in my previous lecture, that in that phase constant the stop band is located as beta equals to pi. So in that pass band, you know that beta equals to 2 sine inverse 2 sine h hyperbolic function, so 2 sine h inverse root over of z1 by 4 z2. So obviously it can be given as 2 sine inverse of this, that f by fc. So this one f by fc sine inverse, that is equals to the pass band. Okay, now we have to find out the characteristic impedance right here. So already it is z1 z2 into 1 plus z1 z2, because zsc and zoc, if you are multiplying and root, then it is a zot. So for T network z0, so what is the value? That is here you can see that this value if evaluated, so it is like this. So finally it is r0 by f by fc square. Okay, where fc is a cutoff frequency, and if it is a pi network, so the 0 pi is basically this, because one pi network if it is there, you can easily consider it in that form of Y matrix. So Y matrix means basically representing the current pattern. So obviously one z0 pi can easily represented by that Y matrix. If you are taking that Y to Z conversion, again you can get this. Or in my previous lecture I have shown you how to calculate that ZOT and Z0 pi, for that considering of Z1 by 2, Z1 by 2 and Z2, that is a T network. Again 2Z2, 2Z2 and Z1, this is a pi network. So if you are calculating that Z0 for T and pi, you can easily calculate it by the direct method. So now just putting this value, that Z01 and Z2. So finally what we will be getting, that is R0 by root over 1 minus 1 by fc, this one. So that is the pi and that is T. So we are getting two sort of characteristic impedance. One is R0 into 1 by 1 minus into root over 1 minus f by fc square, another is by. So obviously the characteristic impedance obviously for T network is more larger, and for the pi network it is much more smaller. So if somehow the characteristic impedance is required to be increased or to be decreased, you have to select as per what is the T and the pi relevance for this. Now if you are equating these two equation, it means if you are equating 1 and 2, so that 1 and 2 if you are equating, so that fc is given and here it is lc given. So by this, that the help of these two, if you are multiplying this, so obviously L into pi, that is equals to fc r0. So in the same way, that what is the value of that L, say it is pi fc, that is r0, that is h. So finally that value we have calculated for L for low pass filter, it is this. And what is C, you can easily calculate it, just instead of multiplying you should divide it, and finally you will be getting that C equals to 1 by pi, that 1 by fc multiplied with 1 by r0. So 1 by pi fc r0 farad, that is equals to f, and that is equals to L. So you have to give this value accordingly, otherwise the filter will not work. So finally I mentioned right here, where R0 is the characteristic impedance and image and constant k value is supplied. So how the filter will look like, just see this, that here it is Z1 by 2, Z1 by 2, Z2, that is you can say here it is L2 right here, and this is Z1 by 2, this is Z1 by 2, that is Z2. Now you have to consider in the other way, what is that is Z2 by 2, that is Z2 by 2, that is 2Z1, it means L. So it is a pi model, it is a T model. Okay, so that is a low pass filter. Now parameters to be designed for the high pass filter, if you are doing this. So in the same way, how you have to consider the high pass filter, there the FC will not tending to 0, it is tending to infinity. So here the R0 equals to same as it is root over L by C, this one. So cutoff frequency here Z1 equals to j omega c for Fc tending to infinity, or Fc equals to 1 by 4 pi root over of Lc. So what is the range of that Fc? It must be lying between 1 by 4 pi root over Lc to infinity. So that is the high pass filter range. So what is the attenuation constant here? For the pass band alpha equals to 0, and for the stop band alpha equals to this, that is 2 cos inverse Fc by f, and that alpha equals to 0. So what is the attenuation constant for that low pass? Here it is this cos inverse h f by fc. Here for that high pass it is, you can say that is cos inverse fc by f. Okay, that is f by fc, so it is fc by f, and beta equals to 2 sin inverse fc by f, whereas the beta for the low pass you can see that is f by fc. So just reverse of this. So alpha and beta is just a reverse in that case of high pass and low pass filter. So you have to put alpha equals to 0. So finally find it out the pass band, and the stop band has to be given like this. So what is the characteristic impedance? Here that f by fc is just reverse. So you can see this, it is f by fc r0 for t and pi. Here for t and pi it is z0t and z0 pi, that I want to mean right here. In this particular equation you can see this is fc by f instead of f by fc. In the second case it is also same, that is fc by f here. So the pi network, the pi and t network for the high pass filter is characteristics like in this way. So the question may arise that if this is so what is the construction for this? You can easily see this diagram, and there say L and C can be easily calculated. What is the value of L and C? Right here we have already calculated that L equals to this k and 1 by this. So it is a constant k type filter. K equals to what? Root over z1 z2. So it is can be easily calculated having that k value. So omega L and omega C, so k equals to root over L by C. Just put this value of k and you will be getting easily what is the value of L and what is the value of C. So what is the consideration of that high pass network? So it can be easily constructed in the pi and t proportion. So if you are considering that pi proportion, it like this, C 2L 2L. So what is the value of L? You are finding out by this method what is the value of C. Just put this in a pi form, you will be getting the pi network. In the case of T network, the C will be doubled here, 2C, here 2C, and that L, what is 2L, right here is L. So the same value can be implemented to this to get that T network, or you can take some Z transformation, you should take some Z parameter or Y parameter transformation on this particular one. You will be getting easily what is the design schematic of that high pass filter in that pi and T formation. So in the next class we will start from that active filter over the passive filter, and what is the active filter, how the mathematical problem is done on the active filter. So thank you very much, and see you all in my early class for the last lecture on that active filter over the passive filter, and that is the end of all. So in future I will add more mathematical example on that worked out mathematical example. You may better find out in my class lectures or in YouTube also, that I will publish many more mathematical problem on that active and passive filter. But the basic things, how to solve the problems which is coming from active filter or the passive filter, the basic rule is this, that either you have to do one low pass or high pass filter. I am not going much more deeper of that Chebyshev and Butterworth filter. But if you are doing this, these things are samely dependent on that pi type or like L type or the T type filter. So be with me and find all of you early next in my next class. Thank you very much.